Welcome everyone, and I'd also like to thank Mikhail for his invitation to give a lecture here. It's actually in combination with being opponent for a doctoral exam tomorrow. Of course, anyone who's interested in that, I'm sure was welcome to come to that too. My topic I was going to talk about today, I was told to give a lecture which was, I guess, accessible to a broader range of people. And I decided to choose a title that is Information Networks and Cooperative Communications. So before I begin, as Mikhail mentioned, the chair I have right now is, I'm getting strong support from the Alexander von Humboldt Foundation, so I'm very grateful for that. What I'd like to do here in terms of the talk, I've divided it into three main parts. The first part, I'm going to be talking about information, just very basically, trying to make an attempt at saying what information is, or the way we view it, how information theorists view information. And then I'll talk a little bit about something called network coding very briefly. So I'd like to talk first about information, then about information networks, and try to convince you that information networks are a little bit special. They're different than other networks that you find. There's many networks out there. There's traffic networks. Social networks is a newer object of study. Information networks are very special from these. They're a little bit different, and this difference is quite important and quite fascinating. And the final part of the talk, I'd like to talk about what we mean by cooperative communications, which is then related to information networks. So I've actually already given you the outline of the talk here. First of all, I'd like to talk about what is information. Next, what are information networks and why are they special, and what is cooperative communications? And to begin with, I'd like to take a quote out of a paper by the founder of the area of information theory. So I hope all of you know this person, or at least have read something about him. Claude Elwood Shannon, who founded the area of information theory and the area of modern communications. So what we do today is we use digital communications. That shift is still proceeding right now, at least in Germany. People are switching from analog radio to digital radio, and that's still taking place. But all this, the ideas of why we do this and the theory behind it came about in a paper from 1948. And Shannon passed away a little bit over 10 years ago. So let me begin with trying to answer a little bit the question. Let's think a little bit about what we mean by information. And here's a quote from Shannon's paper. It's a provocative quote, and in fact, every time I've given this or portions of this talk in other places, and every time I put up this quote, I always get some comments afterwards about it. And what he wrote in his paper, it was right at the very beginning, I think in the second paragraph, is that the semantic aspects of communication are irrelevant to the engineering problem. The significant aspect is that the actual message that we are trying to transmit is one selected from a set of possible messages. And the usual, I think the usual reaction is, well, no, of course, semantics are very important, or you think they ought to be. Just as an example, here we have 4 pieces of fruit, an apple, a banana, a pineapple, and an orange. And you'd think that that should play an important role, right? If whether we are choosing an apple or a banana, for instance. But what Shannon said is no. For the engineering problem, this is not important, and I'd like to represent that here just as I've shown it. We could equally well, if we wanted to transmit the message which of the 4 pieces of fruit we chose, we could equally well say we chose the letter A for apple or B for banana. Or even more simply, we could represent each of the pieces of fruit by a bit sequence. In this case, 4 possible bit sequences, 00, 01, 10, or 11. The important point here is that any of the 3 sets can represent the 4 types of fruit equally well. So the semantics do not play a role. And information theorists prefer bits, so it's the simplest representation. And in fact, I'm not sure how many of you are familiar with this, but the word bit, which I think is very commonplace in our society today, first appeared in Shannon's 1948 paper, and it represents the two words binary digit. It's a word suggested to Shannon by John Tukey, who was working at Bell Labs at the same time. For those of you who know something about Fourier transforms, he was one of the co-inventors of the fast Fourier transform, although of course the fast Fourier transform really goes back many years earlier to Carl Friedrich Gauss, who was using this to track planets. So he had invented the fast Fourier transform many years, I guess I should say many tens of years earlier, hundreds of years maybe, it's going a little too far. In any case, information theorists prefer bits. So now the next question we could ask is, well, okay, if we're talking about information, what is a bit of information? And to describe how communications or information theorists, what they call a bit of information, we have to talk first about something called entropy or uncertainty. And to describe that, a good place to start is to look at one bit, two possibilities. In the simplest case would be to take, for example, a coin, a fair coin C, that has two equally likely possibilities, and I think it's very natural to say that the information, or in this case the entropy, the uncertainty, in a fair coin flip should be 1 bit. So that will be our number 1. If we have two coins, C1 and C2, it's natural to think, well, if we flip these two coins, and if they are not related to each other and both fair, the natural thing is to say it's 2 bits. After all, there's 2 coins, 2 bits. And what we are in fact using here is we are counting the number of possibilities that this experiment, the number of outcomes this experiment can have, and taking the logarithm of this number, right? So a natural approach is to say, well, the way we'll count information, or the uncertainty in an experiment, is simply to take the logarithm of the number of outcomes. So in this case, for instance, with 2 coins, there's 4 possible outcomes: heads, 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 tails, tails, heads, tails, tails. So it's natural to take the logarithm of 4, and usually we take the logarithm to the base 2 in communications. And the base of this logarithm, taking it to the base 2, simply defines the units. And as a simple analogy to this, bits are like kilometers, and if we took the logarithm to the base 10, we might be talking about miles, for instance. So that isn't so crucial. What's important is we choose one base, and then we give it a certain units, and if we choose the base 2, we're talking about bits, just like we are here, taking the logarithm to the base 2 of the number of possibilities. Now, this particular measure of information was suggested by Hartley back in 1928. But what's interesting to think about is, well, this definition is natural, I think, if the experiment we're doing here is fair. So if our coin is fair, I think it's natural to do this. But then we can ask, what about biased or unfair experiments? Should we still continue counting in this fashion? So for instance, suppose we do the following experiment. We ask the question, you ask the question, does my partner love me or not? Right? And perhaps you are uncertain, you know, maybe not 50-50, right? But if maybe you hope the answer is yes. And let's just say the number is about 90%. So in this case, 89%. And the probability that you will hear no, for whatever reason, is 11%. And you can now ask the question, well, how much information, how do I quantify the amount of information I've received when I get this answer? So how many bits does her answer give? And I'll write here down right away. Well, Shannon says the amount of information you get out of this answer, or the entropy, the uncertainty you have about this answer, he would measure like this. It will be a sum, p log 1 over p plus 1 minus p log 1 over 1 minus p. So for instance, a fair coin would have the probability of both answers being 1/2. So if we insert that into here, we'll get a half. The logarithm of 1 over 1/2 is the logarithm of 2. Logarithm to the base 2 of 2 is 1, so we get a half here. And of course, here we're just getting the same thing because 1 minus a half is a half. So we get a half plus a half, we would get 1 bit of information. That's consistent with the counting rule that we had before. However, if our answer, if we're not certain about what the answer will be, and we're not certain in a biased way, then here we would compute this as following. P here is 0.89, logarithm of 1 over 0.89 plus 1 minus p is 0.11, logarithm of 1 over 0.11, and if we compute that, it's exactly half a bit. So now you say, well, great, now I know the amount of information I'm getting from the answer is half a bit. Well, what does this mean, right? I mean, in any case, you can ask yourself, you know, perhaps how much entropy do you prefer in the answer, right? So if you get the answer to the question, do you love me or not, and you believe it's with probability half, you would get the most information from your partner this way. Right, so you can think about that for the moment. Let's just keep going. So Shannon's entropy, then for a general experiment, the way Shannon suggested to measure entropy was as follows. We would take the sum over the probability over all possible outcomes times the logarithm of 1 over the probability of each particular outcome. So that's the sum over k, pk log 1 over pk. And the way what we call information today is the amount by which an observation reduces the uncertainty that we originally have on average over all possible answers we could get on average. So that's what information is. So let's take a look at our experiment again. Suppose the answer yes, we look at that. Well, what is the information? What's the amount by which the observation, so the answer to our question, do you love me, how much do I reduce the uncertainty? Well, if we get the answer yes, it would be the original uncertainty minus the amount by which our uncertainty has reduced when we get the answer. And in this case, we'll just say, well, okay, that uncertainty, if we know the answer, will be 0, right? Because once we know the answer, there is no more uncertainty. So in this case, the information for this answer, the information we get is exactly the original uncertainty. If we get the answer no, well, it turns out to be the same because we'll get the original entropy and the amount by which the entropy is reduced by the answer no. Well, again, that difference again is the entropy. And so the information we get out of this experiment, the way we would measure it is the average of these two. So it would be here, it would be 0.89 times this entropy plus 0.11 of this entropy. Well, that's just the entropy itself. So here we would call the information between the original object and after we've received the answer, we write that as this. The information between love and love is the entropy of love in this particular case, the uncertainty of love. More generally, however, an answer may still leave you with some uncertainty, right? Because it could be your partner is teasing you, right? And you may not be sure, is my partner teasing me or not? Or perhaps you don't quite trust your partner, and then there might still be some uncertainty even given the answer. So more generally, for an experiment, we measure the mutual information exactly in this way. We take the uncertainty that we originally have before we get an answer, we measure the average over all possible answers we get of the uncertainty once we get that answer, and we measure the difference. And that's the amount of information. That's how we quantify the amount of information we get out of an experiment. So as a simple example, suppose you know for sure your partner loves you, right? If we know that ahead of time, well then the uncertainty of love would be 0. There is no uncertainty. So irrespective of what answer your partner gives you, yes, no, there's no information. Because after all, if your partner says no, you know they're teasing you. If they say yes, you know they're not, because you know it ahead of time. So there's no information sent. So it's interesting. If you prefer the latter situation, you will get no information out of your partner if you ask them the question, do you love me? Perhaps that answer has some other value to you, but there will be no information in it. Okay. Yes, and then just made a small. Usually in the communications and information theory communities, we give this the name mutual information because it turns out that it's symmetric, but that's just a small aside. Okay, so given that, so this is how we quantify what we mean by information. The next question is, if we go back to the technical aspects of the problem, is what value does a quantity like this have? And the remarkable thing is that these quantities, such as entropy and mutual information, have very important implications to what we can do with data. For example, if you have a file, such as a PDF file or a text file, It turns out that the rate to which you can compress, the amount by which you can compress this file has to do with the entropy, the uncertainty you have about the text. Mutual information, this quantity of information shows up in reliable communications. So for instance, if you have your cell phone and you're communicating with a base station, in this example I'm giving a little bit of a different example, perhaps I should go to that. Suppose we have the internet, you want to send some email packets to your colleague or friend, but what happens is these packets go into a network, and when they go through some computers, these computers might be busy, and they might be so busy they'll drop the packets. Right? And then your colleague or friend will receive some of the packets but won't receive others because they may have been lost in going through the network. And so suppose you send the packets P, but what your colleague receives is the packets here script P, then it turns out the amount of bits of information you can give your colleague turns out to be the mutual information between the packets you send and the packets that your colleague receives. So that's a remarkable fact. And not only that, to be able to get close to this ultimate limit on communications performance, you have to use very sophisticated coding methods. And we'll be talking about some examples of coding in just a second. So if I was going to state this more precisely, and I write here in engineering English, part of the reason that came up, I gave this talk in German up to now in Munich before, and there, of course, the engineering English plays a role from the language perspective here, perhaps too, if you don't have a communications background. So more generally said, and in a very technical sense, this is the basic model Shannon looked at in his 1948 paper for reliable communications. There's a source that puts out a certain number of bits, and he assumed that these bits, in general, you could assume these bits are biased, but we will assume here they are fair coin flips. There's a message which has a certain number of bits, so there are B bits here. There's a vector that a vector of symbols, a sequence of symbols we send into a channel. What comes out of the channel, so you can think of these as your email packets. What comes out of the channel are other email packets. For instance, some of these could have been lost. And then at the receiver, you try to recover from those packets you receive the original message. Usually one also adds something called a cost constraint to this problem. What this means is, for instance, usually the transmitter might have some energy constraints. Often in wireless communications, we measure energy by viewing this X as a sequence of real or complex numbers and then taking their square. And the sum of the energies in this particular example would have to be less than some upper bound for some cost function S. In this case, in this example here, the cost function S would just be the quadratic value of the first position. And the problem that Shannon solved is to find the maximum rate for reliable communications. That is to say, he wanted to make sure that the error probability was small, but try to maximize the number of bits that was transmitted in a certain number of uses of the channel, a certain number of times that we use the channel. And his answer, and that's what I was referring to before, is that you can transmit reliably up to the mutual information between the input and output. So again, what this is the entropy of the output, and what you subtract off is the entropy of the output on average after receiving a certain sequence of symbols. And so, and then it turns out there's an optimization problem involved here, but it turns out this number is very important for reliable communications. Okay, that was one technical slide. Let me now move on to that's what I wanted to say about information. Okay, so we measure information in an experiment by looking at entropies or uncertainties and how much these entropies change on average when we get an answer to an experiment. An outcome of an experiment. So the next thing I'd like to talk about is try to answer the question, what are information networks? Now, you experience networks every day. For instance, there's the telephone network. You probably use your telephones. There's a fiber optic network that underlies this telephone network. There's your cell phones, mobile radio networks. There's traffic networks. There's distribution networks for corporations that have to buy goods, store them somewhere, and then later ship them off somewhere else. And what I'd like to convince you of in the next couple of slides is that information networks are very special because bits are not commodities like cars or trains and so forth. So what is it? First of all, let's talk about a little bit about what a network is. Usually a network you represent by a graph. So for instance, here we have a picture of 12, every picture here is supposed to represent a person, so there's 12 people. And what a graph is it's a set of nodes like this and a set of edges between nodes, and usually the nodes represent something like a person and the edges represent something else. For instance, here it might be friendships between people, so this would be an example of a social network. We represent this with a graph, which is a pair of nodes and edges, where an edge usually represent by a pair of nodes because it's a line going between two particular nodes. Now, often we are interested in graphs that have something called capacities. So in this particular example, I'm looking at a traffic network. This particular traffic network has 4 nodes. What does a node represent? Well, it might represent an intersection here. This intersection has streets coming into it. So in this example, as compared to this one, here I had edges that were undirected, because friendships you would probably view as being going both ways. Often, though, we look at graphs, it might be interesting to look at graphs that have directions, where the edges have directions, like if this was a one-way street. So often, what we do then is we order the pairs, right? We write the 1 first and then the 3, whereas 3, 1 would represent a street going the other way. Okay, so now what happens is we often label edges with something like capacities. In this example, how many objects, in this case cars, can flow through each edge in any particular time unit. Okay, so for instance here, here I've labeled every edge with a number, like 30, and this number may represent how many cars can travel through this street every minute. Then we talk about flow rates, traffic flow rates. We can now ask, suppose we have red cars beginning at node 1 and going to node 2, and blue cars going from node 2 and then to node 1. By the way, both of these cars are BMW cars. I don't know if you've noticed or not, but they're both made by BMW in Munich. Then we can ask the question, suppose we ask now the question, how many cars can flow between nodes 1 and 2 every minute? Well, here clearly the red cars must first traverse this street. They must go through this street and then go through here and then here. The blue cars, the minis here, must go first through this street and then that street and that street. And the important point here is that there's a bottleneck, right, which both of these cars must share. And the answer is quite clear. The maximal capacity, the maximal rate at which the red cars can go from 1 to 2 and blue cars can go from node to intersection 2 to intersection 1 is 10 cars per minute, either blue or green. Okay, and this would happen if this was a water network. This would happen if this was a distribution network, a railway network, a network where people walk through, whatever. The classic networks that people consider, this would be the maximal rate. And what's special now about information networks and what makes them different than all these networks is that this answer changes. Okay? And the reason it changes is because we can do with things like bits things we can't do with goods or cars and so forth. So let's take a look at the same network where every node represents a computer or a device, and every edge perhaps represents, let's say, a wire with a certain capacity, a bits per second limitation. And now we can ask the same question. Suppose the red modem wants to transmit a certain number of bits to the black modem and vice versa. What's the maximal rate at which we can transmit bits? It turns out now that both devices can transmit to each other at the same time 10 megabits per second. So it's not either the red bits or the blue bits, it's both bits at the same time. And actually the trick is quite simple once you see it. What you can do is node 3 helps node 1 and node 2 to transmit. How does it do so? Well, this device here will send at 10 megabit per second to node 3. This device at 10 megabits per second to node 3. Node 3 collects these bits, and it can do the following with these bits. It can add them up. And by adding up, I mean 0 plus 0 is 0, 1 plus 1 is 0, 0 plus 1 is 1, 1 plus 0 is 0. So it's a modulo 2 addition. It sends this modulo 2, so it takes bits 1 and bits 2, it adds them up, sends them at 10 megabits per second through here. Node 4 simply passes those on. It copies that bit stream, passes it on both directions. And now if we look at node 1 knows B1 and receives C and can simply add its own bits to this sum. B1 plus B1 will cancel because 0 plus 0 is 0, 1 plus 1 is 0, and it will simply able to come up with B2, and node 2 can do the same thing at the same time. Right? So with bits, we can actually put them together to create a new bit. That's the important distinction in information networks. So this kind of observation, which remarkably isn't that old, it only goes back to a little bit over a decade, or at least looking at it in a systematic fashion, has led to a lot of research in the past 11 years in the information theory area and communications area. And there's very many beautiful results using sophisticated mathematical tools involving Galois field algebra, of which this binary addition is an example. It's just the simplest kind of Galois field of size 2. Okay, so this type of method is called network coding. Perhaps some of you have seen this before, but perhaps others have not. Yes, so this is what I wanted to say about information networks and why they are special, different than other kinds of networks. The difference that you have in information networks leads to a lot of interesting mathematics, but it also leads to new communications methods which are being developed right now. Okay, now this brings me to the last topic I wanted to talk about, and that is try to answer the question, what is cooperative communications? And in fact, you've already seen this. If we look at this example, node 3, to be able to do this kind of operation, has to decide, I'm going to help node 1 and node 2 to transmit their information. Node 4 must also decide to help by copying these bits and perhaps even using twice the energy that it needed to use before, because now it has to send bits in both directions at the same time. Perhaps that requires more energy than before. So in other words, nodes 3 and 4 must agree to cooperate with nodes 1 and 2 to transmit bits. Hopefully, this cooperation will, in the end, benefit everyone. But of course, that's not clear ahead of time. But this has to do now with the question of cooperative communications. So cooperative communications refers to network communication where nodes cooperate rather than compete to transmit data for themselves and others. For example, the network coding for the classic information networks we just saw. But an interesting question too, which gets quite a bit more sophisticated methods than the example we just looked at, is to start looking at wireless networks. How can we apply these ideas that we just saw for these classic networks, can we apply them to wireless devices as well? And can you also come up with new methods? So I've shown a simple example here. Suppose you have your iPhone and you want to transmit your information to some base station. You may have one wireless device here which can pick up that signal, perhaps another wireless device over here. How could these nodes help the transmission from the iPhone to the base station? What kind of methods can we use? And it turns out there's a whole area of, within the information theory area, there's a specialized area called network information theory that deals with the fundamental limitations of this type of problem. And in going to network information theory, I'd briefly like to introduce you to two personalities from our community. One of them was Professor Alsveda. He's unfortunately passed away a little bit less than a year ago, but he made an enormous number of contributions to the area of network information theory. He was the only German Shannon lecturer. So in the information theory community, there's this distinction of someone who, for their lifetime contributions to the field, the highest honor the Information Theory Society of the IEEE can bestow on its members is to become a Shannon lecturer. He's the only German professor who has ever been a Shannon lecturer. Next year's Shannon lecturer in 2012 is this gentleman here from Stanford University, Abbas El-Gamal. And he also made an enormous number of fundamental and important contributions to this area. In particular, he developed something called cut bounds for information networks. And I don't know how many of you are familiar with this, but for transportation networks, a lot of work was done during the Second World War on transportation networks. As an example, which is a little bit morbid, but I'll give it anyway, is suppose we have a rail transportation network. Which rail lines do we bomb to make sure that the enemy cannot transmit its goods to the front? Okay, and which ones do we bomb? So we look at what's called a cut in the network, and you try to find the minimal cut that way we have to use the minimal number of resources, the bombs and airplanes and so on, to prevent goods from being transported to the front. These kinds of bounds can be extended to information networks, but you have to be careful because things like that network coding I just showed are possible in information networks, which are not possible in these in these other networks, like transportation networks. So you have to take some care in developing the theory for that, and this was done by Abbas, I think a little bit after his PhD thesis. A lot of work these two gentlemen did too involved network coding. This is actually Professor Alsveda was one of the people who pioneered this, and relaying strategies. So I'm going to focus a little bit on this, and this is an area that Professor El-Gamal developed the basics of this area to a large extent, along with his co-advisor Tom Cover. Okay, just to give you an example of the way this looks, again a little bit of a technical slide. Suppose we have a very simple network. You have two people, say, talking over a telephone network, and both want to exchange messages with each other. This is called a two-way channel, and Shannon looked at this problem in the end 50s, early 60s. So here we have two messages. Before we only had one message going from the left and destined for the right. Now we have a channel that takes in two sequences and puts out two sequences, because after all, a lot of communication is two-way, right? You're talking with someone on your telephone, you say something, they answer, and so on. So the communication is two-way. Turns out that this simple problem, simple-looking problem, is much more difficult than you might think, and it's in fact still an open problem, what the ultimate rates of transmission are for this class of channels. One of the remarkable open problems in information theory. Now, Shannon gave a bound that looks like this. It's effectively a bound that, if I can describe intuitively what this means, is you split the network into two, and you measure how much information is flowing from the left to the right, given what the right knows. So it's the amount of information between the input here, the output here, given what this side already knows. That's what this conditioning here means. And similarly, the maximal rate in transmitting from right to left is upper bounded by a similar expression. And El-Gamal took this idea, in some ways, I suppose, I should be careful how I say that. For general networks, you can do the same. What you do is you take a large network, you split it into two pieces, and you measure the amount of information flowing from one side of the network to the other, given what the other side knows, what's the amount of information flowing from or going from the right to the left, given what the left knows, and you can come up with similar bounds for networks. But it wasn't quite as simple as just taking this example and applying it to networks. You had to be a little more cautious in how you develop these bounds. So Professor El-Gamal developed a bound of this sort, and the important thing to realize is that this style of bound in measuring information will apply to any kind of network involving information. It could be a biological network, how much information is flowing from one cell to another, or a set of cells to another set of cells. It could be a physical network. It could be a financial network. It could be a social network. Anywhere where we're measuring information, how much information is going from if there's information flowing in a network, these tools apply to any of these networks. It's a very general framework. I added a small asterisk. That's one area I was interested in working on, and together with a colleague at the University of Texas A&M, we developed some strengthenings of these bounds using something we called edge cuts, as opposed to the cuts that are used here. Anyway, getting back to the problem that we were looking at in this picture here. Okay, so what we have here, getting back to this, is we really only have one-way communication. We have this iPhone trying to communicate with the base station, and what these nodes do is act as relays. So let's look at that for a moment. It's a similar style of model as we originally saw, transmitting bits from one side of the network to the other. What we have here is one additional node that we call a relay that gets information and tries to help node 1 communicate with node 3. And it turns out, like many other problems, network problems, this problem is also still unsolved. It's one of the most famous open problems in network information theory, to try to find the capacity of this relay channel. And it does have practical importance for wireless communication. So let's talk a little bit about what kind of things could a relay do here. Suppose this was a waveform. This was an electromagnetic waveform. It's propagating out into the channel. The relay sees some noisy version of this waveform, so does the final destination. What can the relay do to help the original wireless node send its information? Well, there are several natural things that it could do. It could take the electromagnetic waveform and simply amplify it, right, and then send it on again. So it doesn't do any kind of sophisticated processing. This is called amplify forward, an amplify forward strategy, a very basic strategy, one that is the easiest to implement of all these strategies. Not necessarily easy to implement, but it's the easiest to implement of all these strategies. A second natural strategy is, well, perhaps the relay is right in between the transmitter and receiver. So a natural approach would be for the relay to decode, to get the message, re-encode it, and pass it on. Okay, and this is called a multi-hop strategy, because you're doing 2 hops, right? First to the relay, and then from the relay to the destination. This is called a decode forward strategy. But there's a third strategy, which I think is rather non-intuitive until you begin to think about a little bit what it means, and it's called a compress forward strategy. So I think the way you might be able to think about this is as follows. Suppose I'm trying to communicate with one person at the back of the room, and I have one person close beside me. That person will be able to understand what I say very well, right, and can actually decode what I say. And then we can both together shout to the person at the back of the room, and that person will be better able to understand what I wanted to say in the first place. Okay, so a natural situation where you would use a decode forward style of strategy is if the relay is close to me, right? Because that person can understand very well what I say. However, if the relay is a person sitting at the back of the room, right beside the gentleman I want to send my data to, then neither of them will understand me, right? So it doesn't make sense that the relay tries to understand what I say. Instead, what they should do is start talking with each other and exchanging messages. Since they're close to each other, they won't require a lot of energy to do that. They could even whisper to each other, say, what did the person at the front say? The other person, what did the person, oh yes, I understood this. No, I understood this. And after a while, they figure out what I said. And it's this third style of strategy, which is what compress and forward does. This is a situation where the helping device is far away from the transmitter. It does not try to decode, because it cannot do this by itself. Instead, what it does is it takes the waveform, compresses it, quantizes it down to another waveform that requires less energy to transmit, and sends that off to the final destination. That final person now has 2 sources of information, one from the partner and one from myself. Okay, and it's a very natural strategy once you think about it from that perspective. And this is called a compressed forward strategy. So what the relay does is it quantizes, it compresses what it heard. And in technical terms, it can do a couple of other things. It can hash this message. Hashing simply refers to taking a long bit stream and converting it to a shorter bit stream. So you do that, for instance, when you have digital signatures on your document. If you have your document, it's a long document, maybe 30 pages, with a lot of bits, you add a digital signature by compressing this document to maybe 16 bits, or perhaps 32 bits, and you add that to the end of the document, and that's like a check on your document. So that's a hash of the document. So what I'd like to talk about now, and this is a little bit more for the researchers in the room, is there have been, so all these two strategies were developed decades ago. This one has been used for a long time already in certain communication networks. There have been two recent improvements on this last method, and my motivation for showing you this is to relate to the network coding. It turns out that this first method that was developed recently properly generalizes network coding from classic networks to general networks, including wireless networks. And I say properly because if you apply this method to classic networks, you would recover exactly the network coding results that are already out there. And I think that's an exciting thing because a lot of the things that we've developed now for classic networks using sophisticated algebra, for instance, Galois field algebra and other things, we can now at least think about how to extend that to other networks, any kind of information networks, including wireless networks. Finally, I'd like to show you an even more recent improvement on this method that I was partially involved with. Okay, so let me describe to you what this method here does for a for a wireless network. So suppose we have a source device. It's transmitting a waveform, trying to transmit its information. The relay, and this is common to a lot of practical relays, it can either listen or transmit, but it can't do both at the same time. The reason for this is usually you're transmitting with much more energy than with which you're receiving, and if you're transmitting and receiving on the same time on the same antenna, your transmitted signal will wash out the signal that you're trying to hear. So usually it's not possible to do both at the same time. There are some devices that can do this. So let's just suppose we have that kind of device. So then what we could do is as follows. We divide communication into blocks of time. So this represents time. These two blocks represent what the source node is transmitting in every block. So for instance, suppose we have a message M of a certain number of bits. We map that message onto a vector that we send into the channel. This vector represents the electromagnetic waveform. The M is bits, X represents an electromagnetic waveform. And the source just in every block maps its message onto a waveform, sends it. Next block maps the same message onto a new waveform, sends it, and keeps doing this. Okay? Here we'll just look at two-block transmission. The relay, first to be able to do anything, it must listen before it talks, right? So it first listens, that's what this 0 represents, but then it can already start processing based on what it heard, and based on what it heard, it quantizes what it hears, the waveform it hears, to bits, Q, that represent, yes, so it quantizes it to bits. These bits represent a coarse version of what it heard, and then it encodes those bits into a waveform it itself transmits into the channel in the next block. So then it transmits this X22 as a function of these quantization compression bits. After these two blocks are completed, the destination is always listening, and after both transmission blocks are completed, it will try to decode both the quantization bits and the messages together. After it's decoded both together, it discards the quantization bits and keeps the message bits, because that's what it's interested in. Okay, so that's what this method called noisy, I forgot to mention the name before, it's called noisy network coding. Another name that was given to it is called quantize map and forward, or I like to call it simply quantize forward. That's what this method does. What's interesting about this method, it should be clear. Suppose we had this is one relay. Suppose we had another relay The second relay simply does the same thing. So you'll get a quantization bits for one relay, and then a new set of quantization bits for a second relay. What's interesting about this is that this method actually includes network coding as a special case. Now, it's completely unobvious when you look at this, but it turns out if we applied a method like this to a classic network, we would recover network coding, interestingly enough. Now, there are some problems, or some disadvantages, I should say, with this method. If you notice, what we're doing here is in every block, we're encoding the same message. And if we had a third block, we would again encode the same message. And what that means is to keep the transmission rate constant, this message would have to get longer and longer, right? The number of bits in here has to be efficient enough so that if we use the channel twice over 2 blocks, there have to be enough bits in here so that our rate doesn't drop. So it has to be a long message. It has to have a lot of bits in it. So there's one disadvantage of this method is you have a long encoding delay and a long decoding delay, but there's a subtle disadvantage here, and that is sometimes if you have wireless channels, if you're moving around, and you may have noticed this, sometimes your reception gets poor, right? You watch the bars on your device, you take a little bit of a step to the left, and all of a sudden the number of bars reduces, right? So if we have mobile devices, the channels vary, and what happens here is because you have a long message, it could be that the relay happens to be very close to you sometimes, but because you have a long message, you can't decode it. There's too many bits. That's another disadvantage of this method, choosing long bits. So a simple improvement is, well, let's just replace these long messages with short ones, and that's what short message noisy network coding is. In fact, this is more of a classical encoding approach. This is what's been used in the past. We're just using it a little differently. Rather than sending a long message in every block, we'll take the overall message and split it into small pieces and encode them separately. And then if we use sophisticated decoding methods, it turns out we can achieve exactly the same rates as noisy network coding does. And in fact, this was observed very recently. It appeared in a paper about a year ago at the annual Allerton conference by 2 researchers. Wu is a PhD student, Liang Che from the University of Waterloo in Canada. And they observed this. There's some improvements you can do here. You can use, it turns out to improve reliability, you can change it a little bit by rather than sending small messages, you send long messages after all, but hash it down to short message. And it turns out you can even do something a little better by using joint decoding rather than backward decoding. And this was observed by, especially the second point here, was very recently observed by a PhD student of mine, Ji Ho, at the Technical University of Munich. But the important advantage of using short messages is now the following. If the channel here to the relay happened to be good, the relay has a chance of decoding, right? Whereas if you're using the long message technique, you do not. And just to give you an example of what performance you can gain here, I've here plotted the what's called the outage probability and plotted it against the signal-to-noise ratio. So this is a standard style of plot error probability, outage probability versus signal-to-noise ratio in decibels. It's a standard kind of setup. There's 2 nodes, transmitter, receiver. The relay is halfway in between. There's an attenuation exponent of 3. For those of you who know what it is, that's how quickly the electromagnetic wave loses energy as it propagates along. We have slow fading, Rayleigh fading, Gaussian noise. There's a per node power constraint. We're trying to transmit at 1 bit per second per hertz. And what the plot shows is how well different methods perform. The red curve shows the outage probability, which is higher than the others, of the classical compressed forward method. These 2 middle curves show what you achieve with various versions of noisy network coding, that's the black curve, or some specific versions of short message, the short message encoding, short message method, when you don't try to decode, while if you can decode, because the relay happens to be in a good situation, because the fading is strong, then the relay does decode. And again, this is only possible using short messages, not long messages, because the message is short. You gain about 2 decibels in energy, so that's, you're using maybe 60 to 70% of the energy you would have to use otherwise. Okay, so and the gains depend on how high the rates are. The higher the rates here, the smaller the gain, the lower, the larger the gain is. But it's just an example to show you why it's interesting to consider extensions of the methods that were also only very recently developed 3 years ago or about 1 year ago. Okay. One can extend these methods, the short message, noisy network coding, to many nodes, either sources or relays. I've shown an example of that here. So suppose the relay is not only trying to help another node, but is also transmitting its own information, then it can do so. And what's nice, again, the noisy network coding method extends network coding to general networks. This is a result of this particular paper where Abbas El-Gamal was also involved with. It turns out you can come up with a very nice rate expression that is related to cut bounds. And it turns out that using the short message version of this noisy network coding achieves at least the same rates, and sometimes can even improve rates because it enables decode forward to achieve even better ergodic and outage rates. And that was shown for many nodes and sources or relays in work I did together with my PhD student. I have one slide which is a little technical. Okay, so maybe I should explain this. What you have here, so this is a rate you can achieve. Effectively, it's a cut bound. You chop a network into two pieces. You have a certain set of nodes S on one side. You have a certain set S hat of nodes on the other side. You get a funny looking difference of informations, mutual informations. Now it turns out for classic networks, what you do, so what is network coding? It's a compression method where you don't compress. It's where where a node, if it receives a signal, it doesn't quantize it. It takes exactly that signal, re-encodes it, and maps it on. If you do that, this Y hat here becomes exactly the YS. These become the same. But the important thing is, in a classic network, everything is deterministic. The Y's are functions of the X's, and all the X's are sitting here. So these X's here determine this Y. And that's what lets us choose this Y hat to be Y, so this term is 0. And now if this Y hat here is the Y, that's exactly the cut set bound with statistically independent inputs, which is the El-Gamal's cut bound on networks. And so as long as every node should be sending statistically independent signals, as happens in classic networks, you achieve the cut set bound. You know, it's very simple. Once you have the expression, it's very easy to get to the results you want to. So that's for deterministic or classic networks. For Gaussian networks, such as for wireless, there are some nice results that show that if you compress using a simple Gaussian style of compression method, you can get within 0.63 times the number of nodes bits of capacity. Why is this important? Is because often one is interested in high signal to noise ratio, and then this is virtually optimal. Again, though, however, there's some problems inherent to long messages. The encoding and decoding delays are large. Yeah, okay, this is a subtle point, but the important inflexibility is that the relays cannot use multi-hop or decode forward. So this brings me to my second last slide, and we can ask now, well, so we have these sophisticated new relaying methods. They've been developed only within the last year to 4 years. As an engineer, you're always interested in the question, well, can we use this? Can we build this into mobile devices? Can we build this into base stations and so forth? One important advantage of this noisy network coding method is that the devices, the relays, operate autonomously, right? All they're doing is they're receiving an electromagnetic waveform and quantizing it. They don't need to know what code was used. They don't even need to know the bandwidth of the signal that was transmitted. They don't know whether they don't need to know whether it's a GSM signal or an LTE signal. They quantize and forward. Right? So they don't need to do any kind of operation. They can do operations which are independent of at least certain aspects of the technology that's used. So relays can operate in a distributed and autonomous fashion, very important advantage. It turns out they can achieve what I call the multi-output gains of multi-antenna transmission. What that means is if this node is close to the receiver, you effectively have a 2-receiver array, and that's the performance you'll achieve. Using the short message version of this approach, we can also achieve the multiple transmit antenna performance, because now this node, because it's close to here, it can decode. So you can also achieve the multi-input gains of MIMO. So that's why I think this method does have real advantages, especially if you want to operate in distributed autonomous fashion. But of course, I should take that, be a little careful for that. If you do decode, then you do need to know the technology again, right? Because now you need to know what kind of code was used. You need to know whether it was LTE or GSM and so forth. Perhaps that's a little easier to do because these are close together. What's important too is that the method applies to more than radio. It applies to any kind of networks. It applies to classic networks. The method applies to optical networks too. So it's independent of what you're doing. It applies to any information network. This kind of method applies to biological networks, applies to financial networks, and so forth. Any kind of network where you're trying to transmit information. The difficulty, I think, that one faces now, especially if one wants to apply this to wireless networks, is how do you design the coders and decoders for these boxes? And especially the decoders seem to be the problem, because the only method we have right now at the base station to be able to get the message back is you have to consider the entire network together. And so you have to know which nodes are operating the network, who is transmitting what, and then do a big joint decoding of the whole thing, which seems to be difficult to implement. But okay, we've been here before, right? I mean, the challenges of building good decoders have been there before. Perhaps someone will come up with some good methods to make the complexity reasonable. So this brings me to my final slide. It's just a slide of some of the activities that we do in Munich, some of the research we're involved with. Various topics we are looking at, but the core is really using the tools of information theory, communications theory, and coding theory. There's a lot of interesting work on radio with low energy transmission, something called timing codes. We have a joint project with the Deutsche Luft- und Raumfahrt, the German aerospace, applying network coding to satellite communications. It's really sending two nodes are trying to transmit data through a satellite. The satellite adds up the bits and sends them down. And the reason this is good for a satellite is because a satellite needs to be very power efficient, and so you want to transmit only once down rather than twice, right? So this actually does give good gains for satellite communication. One of my PhD students is just getting interested in distributed storage coding. That's a very fascinating area that's developing very quickly right now. Erasure coding, I have one person working on low complexity decoders. One area I'm very interested in working on right now, based on some experiences at Bell Labs, are trying to determine the capacity limits of fiber optic channels. And I have one student working on some interference management issues. In any case, that's just a very brief overview. So with that, I'd like to end the talk, and thank you all for coming and listening, and I'd be very happy to answer any questions you might have. Thank you.